It's more on probability distributions. So this is a Bernoulli distribution. It's a very simple distribution. It's a discrete distribution. And it's one where there's only two outcomes, 1 or 0. So it's binary. 1 usually represents success, 0 represents failure. So we're going to let x represent our random variable. The density function will look something like that. Probability that x equals x. Well, we'll say the probability is p if it turns out to be success, so x equals 1. And therefore it's 1 minus p because it's the only other outcome if x was equal to 0. Of course, another way we could write this is just using this little formula. Because remember, x can only take on the value of 0 or 1. So if x is 0, then we would get 1 minus p to the power of 1, which is what it says. And if x is 1, we end up with p, again, which is what it says. So we've got a simple little formula for our Bernoulli distribution. There's our table, so we can work out what the expected value and variance would be. So expected value, the sum of the xpx, which turns out to be p. So the variance, expected value of x squared, so that is p, minus expected value of x squared, so minus p squared, which we can factorise to be p, 1 minus p. So to summarise all that, if x is distributed as a Bernoulli, so creatively we go BERN for Bernoulli, and the probability, that's what we put in the parentheses, the probability of success is p. Then the expected value would be p, and our variance will be p, 1 minus p. That brings us to this thing called binomial probability. And all binomial probability is the continual repetition of a Bernoulli trial. So we'll branch off. Remember, there's only two things that could happen. I'm just calling it A and B. So A will be success, probability of P. Rather than writing 1 minus P each time, I'll just call it Q. So Q is 1 minus P. Then I'll do it a second time. We could get AA or AB. And then if I branch off on B, I get BA or BB. Probability of AA would be P squared, then PQ, PQ, and Q squared. If I branched off again, so I do it a third time. So AAA, AAB, and so on. And our probabilities go like so. P cubed, P squared Q, P squared Q, PQ squared, P squared Q, PQ squared, PQ squared, P cubed. And what the heck, let's do it a fourth time. So AAA, all the way down to BBBBB. And we'll put in the probabilities for those. So P to the power of 4, P cubed Q, oh, that's a hard one to say. P cubed Q, P squared Q squared, P cubed Q, P squared Q squared, and so on until the last one's Q to the power of 4. If I'm not actually interested in the order that those things happen, and just how many A's and how many B's, something familiar happens. Well, for one event, that's pretty simple. Probability of A is P, probability of B is Q. With two events, remember, I'm not concerned about the order, so probability of A and B could be either AB or BA. I get 2PQ, but have a look at the values. P squared, 2PQ, Q squared. 3 events. So 3 A's, P cubed, 2 A's and a B. Well, there were 3 ways of getting that, and that was P squared Q. A and 2B, again, 3 ways of getting that, and that's PQ squared and Q cubed. 4 events. Again, not concerned about the order, and we get P to the power of 4, 4P cubed Q, and so on. And what we've actually got there is the expansion of a binomial. So what we saw back in the binomial theorem. Well, in that case then, we can use our binomial theorem. So X is representing a Bernoulli trial. We're going to repeat it n times, so we've got n trials. We're interested in how many times X occurs. So if it occurs k times, we know it's just going to be that part of the binomial expansion, which was nck, p to the power of k, q to the power of n minus k. Remember, q is 1 minus p. So let's look at some examples then. A bag contains 30 black balls, 20 white balls. 7 drawings are made. Now, the important thing about binomial probability, it has to be with replacement, because the probability has to be the same every single time we do the trial. So 7 drawings are made with replacement. What's the probability of all black? Well, I'm going to let x be the number of black balls drawn. So probability that x equals 7, 7c7, probability of it happening to the power of 7, probability of it not happening to the power of 0. Yeah, for this one I probably could have just gone 3/5 to the power of 7. Essentially it's the same thing. But 7c7, 3 to the power of 7 over 5 power of 7, and there it is, 2,187 over 78,125. As I say, we could have just done that 3/5 to the power of 7. But when we get one like this, I just want 4 blacks. Then I can use the binomial. 7c4, power of 4 to the probability of it happening, power of 3 for the probability of it not happening. There it is, unsimplified, works out to be 4,536 over 15,625. An election, 30% of voters favour party A. At random, an interviewer selects 5 people. What's the probability that 3 of them favoured party A? So I'm going to let x be the number of people favouring party A. We're interested in when is x equal to 3. So 5c3, probability of it happening to the power of 3, probability of it not happening to the power of 2. And we end up with, there it is, 1,323 over 10,000. Majority favour A. Well, now I'm saying when is x greater than or equal to? So 3 situations. X is 3, x is 4, x is 5. Again, just subbing into the formula for each one of those. There's the answer unsimplified. Notice the middle term there. I'm not saying 7.3. That's the dot multiplication. You might prefer to use parentheses. But because 7 was to the power of 1, I did that there, so we don't look at it and think of 73 to the power of 4. I suppose you could put 7 to the power of 1. That would be another way of distinguishing it. Calculating it out, 4,077 on 25,000. At most 2 favoured A, well, we still use our probability theory. That's the complementary event of what we just worked out. So it'll just be 1 minus what we just did, 20,923. Okay, let's look at some HSC ones. 2005. There are 5 matches on a weekend of a football season. Megan's taking part in a competition, so a tipping comp. She earns 1 point if she picks more than half of the winning teams for a weekend. 0 points otherwise. So it's unusual rules for this competition. Now we know the probability that she picks the team is 2/3. Show that the probability Megan earns a point is 0.7901 to 4 decimal places. So I need to define what it is, my random variable. So I'm saying, well, x is the number of matches picked correctly. We're saying we want to earn a point. In order to earn a point, we have to pick more than half of the winning teams. There are 5 matches, so therefore I've got to get either 3, 4 or 5 correct. So I'll add those 3 together, but subbing it into our binomial, we get 5c3, 2/3 cubed, 1/3 squared. 5c4, 2/3 the power of 4, 1/3 the power of 1. 5c5, 2/3 the power of 5, 1/3 the power of 0. Bit of calculator work, and sure enough it turns out to be 0.7901. Hence work out the probability that Megan earns 1 point every week of the 18-week season. So now I'm going to define another random variable. This is going to be how many weeks Megan earns a point. So y is how many weeks. We want to know 18 weeks, every week of the 18 week. But we just worked out the probability of it happening is 0.7901. Right, so I guess the big mistake here was people still use the 2/3, 1/3. But no, it's that new probability we just worked out. And that to 2 decimal places is 0.01. Find the probability that she earns at most 16 points. Again, the complementary idea is going to be quicker. So at most 16, well, the complement would be either 17 or 18. We've already worked out 18, but 17 now would be 0.7901 to the power of 17, 0.2099, and we get 0.92. 2007, in a large city, 10% of the population's got green eyes. What's the probability that 2 randomly chosen people have green eyes? Now this is not a binomial probability question. This is simply saying, I got 2 people, they both got to have green eyes. So probability the first person's got green eyes is 0.1, probability the second one, 0.1, 0.01. What's the probability that exactly 2 of a group of 20 randomly chosen people have green eyes? This is where the binomial probability comes in, because either they have green eyes or they don't. So X is going to be the number of people with green eyes. We're saying, what's the probability that 2 have? So out of the group of 20, 2 have got to have them. The probability of green eyes was 0.1, so that's to the power of 2. Not green eyes was 0.9, that's to the power of 18. And we end up with 0.285. What's the probability that more than 2? Again, complementary idea. Well, rather than working out more than 2, let's take away less than or equal to 2. Less than or equal to 2, so either 2, 1 or nobody, and we get 0.32 to 2 decimal places. All right, so that starts us on binomial probability.